Hello everyone, in this video I'm going to take you through how to find a particular solution to a non-homogeneous differential equation when given boundary conditions. In a previous video in this playlist we covered how to find a complementary function and particular integral, so now we're going to put all of that together. So we know the general form of a solution to a differential equation is the complementary function plus the particular integral. And we covered in a previous video how to use these complementary functions, where alpha and beta are the solutions to the auxiliary equation. And then we covered how to find a particular integral by finding an assumed function given f of x on the right hand side of a differential equation. So in example 1, we've been given this differential equation, we've been asked to find a complementary function, a particular integral, and then the particular solution given these boundary conditions. Okay, so we'll begin with a complementary function. And this is when we make the left-hand side equal 0, so we can use the auxiliary equation, which is am squared plus bm plus c equals 0. And in example 1, you can say that a is 1, b is negative 4, and c is 4. So we can solve this as m squared minus 4m plus 4 equals 0. We can factorize the left-hand side, so we get m minus 2 all squared equals 0. So therefore, our solution alpha must equal 2. So now we can look at our complementary functions, and because we've got one repeated real root, we're going to use this form. So we'll say y is equal to a plus b multiplied by x times e to the 2x. So this is our complementary function. To find the particular integral, well, we know that f of x is equal to 2x plus 6. So the assumed function will be in this form, where we need to find c and we need to find d. So we'll say that y is equal to cx plus d. So therefore dy by dx will equal c, and the second derivative will equal 0. And then we'll substitute these three values back into our differential equation. So 0 minus 4 lots of c plus 4 lots of y, so cx plus d, will equal 2x plus 6. We'll expand the brackets, so minus 4c plus 4cx plus 4d will equal 2x plus 6. And then we can equate the coefficients, so 4cx must equal 2x. So therefore, c must be equal to 1/2. And then the constant terms, negative 4c, well, negative 2 plus 4d will equal 6, so d must equal 2. So our particular integral then would be y is equal to 1/2 of x plus 2. So now we have the complementary function and our particular integral. We can put these together, so we have a general solution in this form. The general solution then will be y is equal to, and I'm going to expand out in these brackets, so a e to the 2x plus bx e to the 2x plus 1/2 of x plus 2. The complementary function plus the particular integral. So all that's left for us to do is to find the values of these arbitrary constants a and b. Okay, so for part C, we're going to find a particular solution given these boundary conditions. So the first thing we'll do is that we'll substitute this x equals 0 and y equals 5. So we get 5 is equal to, here we have a to the 2x, but if x is 0, this becomes 1, so we're left with a. We'll substitute x is 0 in here, so all of that becomes 0. The same for the half x, so we're left with a plus 2. So therefore, a must be equal to 3. To work out b, we need to use dy by dx. So we need to differentiate this general solution. So dy by dx, we'll differentiate this term using the chain rule. So we get 2a e to the 2x. We'll differentiate this term using a product rule. So we get bx times 2e to the 2x plus be to the 2x. When we differentiate a half x, we get 1/2. And when we differentiate the constant, we get 0. So now I'm going to tidy up this right hand side. So dy by dx will equal 2a e to the 2x plus 2b x e to the 2x plus b e to the 2x plus 1/2. And we're told that dy by dx equals 8 when x equals 0. So 8 will equal, if x equals 0, this becomes 1, so we're left with 2a. If x is 0, all of this is cancelled. This becomes b times 1, so plus b. And we can add this half. And we know that a is equal to 3, so we can put that as 6. So therefore, b will equal 3/2. So now we've found the values of a and b, we can substitute these back into our complementary function. So we get y is equal to 3e to the 2x plus 3/2x e to the 2x plus a half x plus 2. So this is the particular solution to this differential equation given these boundary conditions. Well, I hope that's given you a clearer idea on how to find the particular solution for differential equations when given boundary conditions. If you found that helpful, please hit the like and subscribe button below, and you can download the full lesson from my website mrmathematics.com. There's a link in the description below. Thanks again and take care.